Well, this is Mr. Pruitt, and today we're going to be talking about the photoelectric effect. The interesting thing about the photoelectric effect was that this is what Einstein received his Nobel Prize for. Most people believe that it's for his theories of special and general relativity, but it was actually his work in the photoelectric effect that brought him a Nobel Prize. So what is the photoelectric effect? Well, the photoelectric effect is a phenomenon that's observed when light of a certain frequency strikes a metal plate and causes electrons to be ejected from the surface of the plate. Now, this was kind of a curiosity back when it was first discovered, and it led to some experimentation. And basically, what happened in these experiments was that they would shine a light on different types of metal, like sodium or calcium or iron or something like that, and they would notice that the plate would release would cause a current in an ammeter. And so in this experimental setup that we're showing here, basically we're shining a light of different frequency on the plate. The plate releases electrons. They hit a second plate that's attached to the positive pole of the battery. Those electrons are attracted to the positive pole, and then as they travel through the wire down to the positive pole of that battery, an ammeter measures the current of these electrons that are flowing from the battery to the plate, from the plate to the battery. This effect that they're noticing causes a problem. You need to remember that that scientists thought that the question of whether or not light was a wave or a particle had been settled with Young's double slit experiment, where we got the wave pattern that showed the constructive and destructive interference and showed that light behaved as a wave. But when they looked at this, when they started investigating this photoelectric effect, scientists would shine different frequencies of light on the plate, basically different colored lights like red light and green light and blue light and purple light. But they only noticed a current. They only got electrons for some of the frequencies. Well, they figured that since light was a wave, that if they increased the intensity of the light, the brightness of the light, how much light was hitting the plate, it wouldn't matter what the frequency was, that it should eventually cause the plate to eject electrons. Unfortunately, that's not what they saw. What happened was that when they increased the intensity of the light, there was no increase in the kinetic energy of the electrons, and so there was no like no matter how bright your red light was, none of the electrons came off. And if you were getting a current with purple light, you didn't get more kinetic energy on your electrons from putting more purple light on it. So that left them with two big questions. The first one was, why does this only happen with certain frequencies? You know, why doesn't this happen with red light, but it does with green or blue or violet light? And their second thing was that, well, if light is a wave, then why doesn't increasing the brightness increase the kinetic energy of the electrons? Well, Einstein had a solution, but his solution began with the work of a man named Max Planck. Planck had proposed a theory of quantized light in his study of black body radiation. Now, this idea of quantized light was kind of out on the fringes of what people thought at the time. What Planck said was that he thought that light came in little bitty discrete bundles, and that worked for explaining what he was seeing in his studies on these black bodies. Einstein picked up this idea from him, and he kind of ran with it. He proposed that light could act as a particle that he called a photon that carries discrete amounts of light energy, and that those discrete amounts of light energy were related to its frequency. Now, the interesting thing about this is that Planck, who was already fairly well established in his career, was so unsure about this idea of quantized light that he wrote to Einstein and said, I'm not sure that you should pursue this line of thought on this, because I'm not really sure. I'm not really sure if I believe this myself, and that while it works in this model, this could basically ruin your career. But Einstein went ahead and moved forward with this idea. So Einstein defined light in the photoelectric effect as basically a beam of photons, a beam of these little bitty packets, these little discrete packets of energy, of light energy, and that each one of these photons carries a frequency, and because they carry a frequency, they also have to carry a wavelength. And what he said was that the greater the frequency of the photons, then the greater amount of energy that they could provide to excite an electron on the metal plate. And through experimentation, they came up with a curve that looked like something like this, where we have wavelength. Remember that longer wavelengths are associated with shorter with lower frequencies. So here, long wavelengths and low frequencies, that the photon had very low energy, but that as we decrease the wavelength and increase the frequency of the photon, that the amount of energy that photon could provide to an electron on a plate went up as an inverse square. So what Einstein figured out was that there had to be a minimum amount of energy that was required to eject an electron from the metal plate. If the frequency of the photon was too little, if it was insufficient, then the electron couldn't be ejected, because the electron would absorb that photon, but there still wouldn't be enough energy there to give it enough kinetic energy to escape the metal plate. If the frequency was high enough, though, like with green or blue or violet light or ultraviolet or gamma radiation, then the electron would absorb that photon, and it would have enough energy to escape the metal plate. And then if there was any energy left over from that photon, then it would be converted to kinetic energy. Now, Einstein called this minimum frequency that was needed to eject that electron from the plate the threshold frequency. All right. So the minimum was the threshold frequency. Anything left over got changed to kinetic energy. Then, looking at the plate itself, he said that the minimum amount of energy that an electron on that plate had to gain to leave to be ejected from the metal, he called that amount of energy the work function of the metal, and each individual metal would have its own work function. Well, so that explains why certain frequencies wouldn't eject it, because they didn't have enough energy to eject that electron from the plate. But what was this about the intensity? Remember, the theory was that if I made the light brighter, if I increased the amplitude of the wave, then I should be able to get more kinetic energy to the electrons. But in Einstein's photon model, the intensity wasn't a function of the amplitude of the wave. It's a function of the number of photons hitting the metal per second. So if you had more photons hitting the metal per second, then you would get more electrons, which was consistent with what they were finding. The problem is that those electrons were not any more energetic. The average kinetic energy of those electrons wasn't changing, and the reason because the average kinetic energy wasn't changing was because we weren't giving them any more energy. Remember, the energy is directly related to the frequency. It's not related to the intensity of the light. So more photons meant that more electrons were ejected from the metal, but since all of them were being excited by the same frequency, since the same frequency was causing them to become excited, then the average kinetic energy of the electrons was unaffected. So looking at these results, most people would say, well, then light must be a particle, and we interpreted Young's double slit experiment completely wrong. But again, it's interesting. The question was, well, did this end up crushing or destroying the wave model? The answer to that is absolutely not. Einstein explained through this that light was light all the time. that it was never just a wave or just a particle. Okay, that light is light. But sometimes its behavior is best explained as a wave, like in Young's double slit experiment. And sometimes its behavior is best explained as a particle, like in his photoelectric effect explanation. So basically, light becomes a Schrodinger's cat. It's something it's two things at the same time. It is both a particle and a wave at the same time. Now, if you think about this, this is really just Einstein's way of letting us know that we don't really fully understand the nature of light at this time. That it has some duality. Anyway, I hope that this was helpful to you, and I'll talk to you next time.